Hello, everyone, and welcome to the compiler reading group. The group hasn't had a meeting in a while, but this is the first one in a while. This time it is a special presentation by Raymond Pasco on the arithmetization of Nock, otherwise known as the even paper. You have the floor, Ray.
All right. So yeah, this is the abstract of the Eden paper. So in previous presentations, I've gone over the standard Nock construction set, the standard Urbit VM. I'll go over that a little again when this paper gets to it. Eden is it's a SNARK VM developed by these four the Zorp team to do to essentially prove execution of Nock. And Nock, as you may recall, is a combinator VM. So I'll start by skipping forward to section 3 and describing what a combinator VM is, specifically what Nock is as a combinator VM, just to reiterate that. So there's one data structure, the native data structure of Nock and also of Eden is the noun. There is exactly one difference between the Nock specification and the Eden specification here. In the Nock specification, a noun is an atom, which is a natural number, or a cell, which is a pair of two nouns. Eden changes this. Eden defines an atom as an element of the whatever chosen finite field is to make it amenable to arithmetization. So you see we have we have this nice little diagram of a tree, right? So they define noun as either atom, which is now a finite field element, or a cell, which is an ordered pair of nouns. And so you end up with this tree structure, right? And there's this standard notation for writing these, which is sort of like const cell notation. It's not like Lisp notation because there's no implicit null terminator. It's just what you see is what you get. And so the only operations that you have are const and then unconst, kind of. You also have the addressing scheme, right, which is described starting at the bottom of this page, right? Basically, just one is the whole tree, 2 is the left subtree, 3 is the right subtree, and then even odd numbers reduce recursively. They also describe in this paragraph here, so I don't need to reiterate it myself, that this is also just if you take the binary expansion of some number, you drop the leading 1 from it, then you get a series of zeros and ones corresponding to left and right from the root. So now I can go backwards and look at section 1. So the point of Eden is to take Nock and make it provable, and they make it provable in a SNARK system. And now I'm not super familiar with SNARK systems or SNARK systems, or what the differences between them are. But the important things are they take the noun data structure and arithmetize it, which I'll discuss in a moment. And they have these interactive oracle noun fingerprints for arithmetizing the operations of consing and deconsing in polynomials. And finally, and also interestingly, the last section of the paper discusses their implementation, which turns out to be stack based, and it also does some tricks to efficiently encode nouns, which are different from the tricks that we used in Urbit to efficiently encode nouns. Okay, so section 2, it discusses the concepts of proof systems. The system they use here is an interactive oracle proof, and it's also mentioned that if you have some good source of randomness, you can turn this interactive construction into a non-interactive construction. And you instead commit to data. So I'm not very familiar with this, but I hope that some people who are might be able to shed light on this in a bit. Okay, so we have SNARK. So I guess SNARK stands for scalable, transparent, et cetera, et cetera, et cetera. There's a basic explanation of this, which isn't too relevant to Eden specifically. And then, okay, so I should have done this earlier. I skipped this, but we have the Nock opcodes, right? So you're always operating on two nouns, a subject and a formula, or equivalently, you can say that you're operating on one noun, which is a cell of subject and formula, right? And it's not it's super important to remember all of them specifically, but the opcodes are 0. The important ones are 0, especially because that's like your memory load. This turns out to be useful later on. You have load from subject is 0. 1 is just constant value. 2 is eval. 3 is test cell or atom. 4 is increment, which is the only arithmetic operation. And so on and so on. Then we have 6 through 11 are just macros. So we have like if then else with subject, et cetera, et cetera, et cetera. Okay, so I'll skip ahead and look at arithmetization basically. So it used this field, the field extension of this finite field cardinality 2 to the 64 minus 2 to the 32 plus 1. Okay, so you use the unique up-isomorphism degree 3 extension f of fp. So it goes up to about 2 to the 192. Okay, the Schwarz-Zippel lemma. I assume that this has something to do. Like I skimmed over most of the parts about arithmetization, but I assume this has something to do with the fact that we can turn things into like polynomial zeros. So we should be able to have polynomials with a degree up to the size of the nouns that can encompass the size of the nouns we're encoding. Okay, the interesting part starts here in section 5.3. So how do we arithmetize nouns, right? We have this binary tree. Each leaf of it could be arbitrary data, and so it's arithmetized into this pair. It's a pair of some binary number which provides the shape of the tree, and then some vector of numbers which provides the leaf values for the tree with that given shape. So that's the deconcoding and then the leaf vector. And this deconcoding of the shape of the tree is pretty simple, right? We just so it says it down here, perform a depth first traversal of the noun and append a 0 or 1 for every move to a left or right. So we have this diagram, right? We have this last thing here as the noun. It's the left child 0, the right child is this subtree, et cetera, et cetera. And so this turns into this deconcoding of 0, 1, 0, 0, 1, 1, which describes the shape of the tree. And each 0 just means go left, right? So we start here. I don't know if you can actually see my mouse cursor. You probably can't. Right. So if you start at the top of the tree, right, you go left, and that's you're done going left. But you go left, so that's 0. You're done going left. And you go right, so that's 1. You go left, left. That's 2 zeros. Then you go back up, go right, etc. So that it's just the order of time of the order of going left and right becomes a sequence of zeros and ones, and this encodes the shape of the tree. And so down here we see, the arithmetization of this noun is 0, 1, 0, 0, 1, 1, which is the shape of the tree, and then the value of each leaf. So 0, 6, 21. All right, if it's an atom, then its tree shape is just the empty string. So these deconcodings have very nice properties here. Namely, we can const them, right? So if we take 2 deconcodings and const them, that's the tree shape is 0, and the left tree shape, then 1, then the right tree shape, which should be pretty easy to convince yourself of, since the tree shape is just go left, then include the left subtree's tree shape, then go right, then include the right subtree's tree shape. And the vector of elements you just concatenate with one another. So the important operation for trees is const and unconst, and you can do these easily. You can unconst in a similar way, right? You can unconst. First you go left, then you keep going until you have finished a complete subtree, and that's your left subtree. Another property of these that isn't on this page is that a valid deconcoding of a tree shape is balanced in zeros and ones. So, and since you're going left first, you know how many ones you're waiting for to have finished an entire subtree. When you've gone left the first time, because it has to include the same number of lefts and rights. Okay, so a valid decword is either the empty string or 0x, 1y, where x and y are valid decwords. Okay, a quick proof that these are just exactly the decwords of binary trees. Okay, because they're and it's just the same thing that I said. This argument here. They're all either the empty tree or some left and right subtrees. Okay, and yeah, this is also the same thing I just said. How do we read it out? We read it out because we know that the zeros and ones have to balance. So the number of zeros encountered so far while reading is at least as large as the number of ones. Okay, so that's and so since we need to be able to unconst them, we need to be able to recognize the valid subwords for left and right subtrees as well. Okay, so this is the first part of the arithmetization. The second part is encoding these as polynomials. And again, we do the we polynomialize them. We polynomialize them according to this scheme here. So we take the same noun again, 0, 6, 21, encoded this polynomial or this tuple of polynomials. So we have length 4, meaning length of the leaf vector is 4. Then we have x to the 4th plus x plus 1, 6x squared plus 20x plus 1. Encoding of an atom is just length 1. It's shape 0, and then value vector is just a. So we see the 6, 20, and 1. Or sorry, yeah. So we see the we've encoded the if we go back, we had this binary 10011. We've encoded it as this x to the fourth plus x plus 1. Then we've encoded the 0621 as this 6x squared plus 20x plus 1. We had a leading 0 there, but we also we include the length in this, the length of the leaf vector in this encoding as well. They mentioned that the length in the encoding is not strictly necessary because you can recover it, et cetera, which is true because you know that the binary Deek word has to balance in zeros and ones, so you know how many leading zeros you have lost just by rebalancing them. But I do think it's better to include the length. Okay, so therefore, you can, in the polynomial encoding, const things, and you can also unconst them. I'm not really sure what they're doing here to unconst them. But consting them is kind of straightforward. You just shift the powers a bit and add them together. And similarly, you do the same thing here. Okay, so then we can then fingerprint them as part of the interactive oracle proof, right? They call this the ion fingerprint. We take some random oracle and I guess we just evaluate the polynomial at some random oracle points. This is where I run into not really being very familiar with how we do this in practice. But if I take them at their word, they can do this, and they can const and deconst things. Then we've arithmetized the noun data structure, which is all you really need to do to arithmetize Nock, because it's just operations on nouns after that. Okay, so we have a compressed tuples into multi-sets. Let's see. I think I actually want to start with 7, then go back to 6. So in section 7, we talk about the actual implementation a bit. So we have a stack machine basically, and what we push on the stack are sub formulas. So if we go all the way back to the definition here, right? You see most of these definitions are recursive, right? The star is the top level knock or top level Eden function, and you see most of these expansions recurse into they have more stars in them, right? You have as many as 3. If you do eval, then you need to eval once to do the subject, once to do the formula, and then the full eval. So you can have up to 3 recursive invocations for one opcode. And so on the stack, we push subformulas and evaluate them. So the stack machine has 3 stacks: a compute stack, which it's actually it holds pairs rather than individual things. In what this seems to mean for them in practice, they talk about it later, is they have this pop2 instruction. Like they handle things on that stack in pairs. And then we have the product stack, which gives us the subformula results, right? And then operation stack, which is the actual instructions for the machine. So they give us this nice walkthrough of the stack machine execution here. Okay, so right, we have a subject formula, and then we have compute product and operation stacks. So what are we computing? Subject formula, product none yet. The initial operation is pop2, which is pop2 off of the computation stack. Okay, op is empty. Op is a Nock op code here. And so they give us this nice walkthrough. For first, the operation is pop2, so we load the operation to subject and formula, inverse cons the formula, and if the head is an atom, we recall from the spec. So A here is subject, and everything after A is formula. So we know if the head is an atom, it's going to be an opcode. Otherwise, it's going to have subformulas. And so we continue to evaluate, push a pop2 on the operation stack for each subcomputation that we end up with, etc. Then perform the opcode, possibly const something. Okay. And actually, I didn't scroll up because they describe it here, right? They yeah, it's a very important column here. Is the operation const? Because that's for the tree data structure, the important thing that we care about is whether the operation is const. Most operations are not const, but const is const. Const doesn't have an opcode, but it's still an operation. It's just you have to const things if the formula is the const is a cell of formulas rather than a single formula. Okay, so we take this table and note that it goes 0 through 5 because 6 through 11 can all be implemented in terms of 0 through 5. So they're not necessarily fundamental. They're available for people writing Nock, and they're available for VMs to possibly optimize since they're very common operations. But they're not necessary to the semantics. Okay, so then we take this table. This table turns into it has these stack effects on our 3 stacks, right? So for example, 2. At 2, I said, if you recall before, I said that 2 recurses 3 times, right? Or rather, it involves 3 evaluations and it recurses twice. So you see, we push, a couple of pop2s on the operation stack, and we do similar things here. Here we have pop2, and const, because this is evaluating the const of 2 formulas means we have to evaluate the formula, the first formula, then the second formula, then perform a const, etc. Let's see. Right, inverse const is memory access. That's true. It's your implementation of 0, which is 0 is like load from the subject, 0 is memory access, is going to be exactly the same as deconsting. To say in this case, they phrased it as, we observe that the inverse const relation can be phrased as proving the memory access is this 0, 2 and this 0, 0, 3. Yeah, so you don't have to do anything additional for inverse const. Okay, here's the noun table. So the urbit equivalent of the noun table is very simple because there's not that many constraints on it. The only thing that you do is you perform a sort of opportunistically computed lazy hash on nouns, and then you share common subnouns in memory. Here you're working with these arithmetized nouns instead. So your nouns go into this noun table. This is the noun table just contains deq words, and it contains leaf vectors as well. You do not store these nouns very much. I'm not sure exactly what they're doing here specifically because they're already well into the polynomial representation by the time they get here. but it's it doesn't seem very alien to me the way that they are the way they're inserting these nouns. Okay, and then subtree accesses. This is essentially our equivalent of a memory cache in this VM, right? If you'll recall, accessing subtrees of some subject noun with opcode 0 is the combinator machine's version of memory access. And so we have these so we have these ways that we turn them into paths. We have tree axes that we can turn into paths. This also this is sort of like a memory cache, and it's also memory constraints, as far as I can tell, like in the constraints for the prover themselves, because what you're proving when you prove a 0 is that that you get the right you load the right thing from the subject, given the subject and access. Okay, and the exponent table. Finally, the pop table. Let's see, the pop table. So we're proving every time that we pop from the stack, is what I understand about this. This section, it might be simpler than I imagine, but I wasn't quite sure what they're doing with this, besides turning every time they pop from the stack into a proving constraint. Okay, input-output linking. The system as described proves only the limited statement. There exists some program P and input I that produce some output. We have to prove, P and I produce O. So this is like an interactive protocol that fingerprints. And as I said before, I guess you can describe it as an interactive protocol and then turn it into a non-interactive protocol by providing a random oracle. Okay, large noun addition. This is also important. In any practical Nock system, you have often very large common subnouns that get shared. You do not want to repeat the standard library in every proof, for example. This is not like a perfect solution. This is a practical solution to this particular issue, in that they just have certain noun hashes that are known. In the case of like an Urbit system, this is actually the case, right? You have Zeus version 420 is in fact a well-known noun, and it's most of what would be repeated. You might have some like 1.6 megabyte noun with 1.5 megabytes of that being the shared standard library. But this isn't like a fully generic solution. They're just saying that they eliminate certain well-known subnouns like this. I guess depending on how much you want to prevent the prover and verifier from colluding, or how much you allow them to collude, you could do better or worse here. Okay, security analysis. The probability of noun collision is investigated here and shown to be apparently fairly low, 2 to the negative 97th, right? It's fine. Okay, constant inverse cons. So you have to homoiconically constant inverse cons the fingerprints, which means that you have to not have collisions in the fingerprints. So they prove that the probability of this sort of collision is sufficiently small, et cetera, et cetera. It's the end of the paper. Was there some think? Oh yes, I was going to go back to this. Yeah, multi-sets. I didn't actually have that much to say about multisets here. I guess I wanted to touch on stacks, like a stack polynomial. So the operations of stacks are themselves put into polynomial terms here, which is how they're able to do things like arithmetize and prove each time that they pop from the stack. Do you see? Was there anything else? Yeah, I think that covers my summary of the paper. I've highlighted some areas where I hope that someone who knows more about arithmetizing things and proving them could shed some light on them for me. But other than that, they have more or less convinced me that they're able to arithmetize Nock.
Cool. Cool. Thank you for the presentation. If anyone has questions, feel free to ask. I have some myself. So how do they arithmetize? Like I understand that they have some like stack machine that when you load something like eval, it like pops operations into the operation stack essentially. So what you just
Yeah,
pop the tree into the operation stack with pop two, and then you just execute the code that was popped, or um,
yeah, you're popping a subject in a formula every time. And since this is Nock, the subject in the formula is the complete thing. And what they just decompose the formula into opcode and rest of formula. Unless it's not an opcode, but instead it's a cell of formulas, then you have to push const onto the operation stack, and then push the sub computation for each for the left and right sub formulas onto the stack.
let me see. How does this affect the original tree? Like originally we had a tree that was like 0 1 0 0 1 to denote the 0621 noun. How does
Yeah,
that kind of like does that get updated in real time after you do instructions, or is that only like an initial encoding to set up the initial polynomial, but then you
it's just like that's an initial. Yeah, that's just describing the initial encoding, right? Because we've shown that we can do the important operations const and deconst on the polynomial encoding.
I see. So you don't need to do anything
So
more
we
because you just need the initial and then it's all
yeah,
good.
yeah. So we perform the consts and unconsts directly on the polynomial representation.
Does anyone else have any questions?
Yeah, thanks for the walkthrough. I found it helpful. Um, one thing that I was kind of not sure about reading this paper is what exactly they do for jets, which, as I understand, are a large part of what makes Urbit kind of practical. And in particular, whether, if I write some complex arithmetic function, which seems a likely thing that people might do in this system, they must be swapping it out for actual field operations somehow. They can't be incrementing by one every time, but it didn't really specify, as far as I could tell, what they did there or how because that requires some connection. It's not just trivial, like the operations, but you have to connect it with the other tables. So that seems to me like a thing that should sort of come.
Yeah, it is not mentioned in this paper, and it is obviously it obviously exists. So a jetted operation is in general it's an operation under the the 11 hint opcode. My guess is that they have they have a compatible way of registering jet, so that they are able to use the same standard library as everything else in Urbit, which provides jet hints in its own particular way.
Do you know if the explicit aim of this project is to provide proofs for Urbit, as in like the current standard librarian system?
Yes, it is. Or rather, its intent is to provide proofs of execution for like the actual Urbit system that's run.
Right, but then they would also need a way of, I assume that some Urbit programs actually use like the natural number range beyond whatever this is.
Yeah, many do. Like, right, that's the other question that I have is if you limit to the range of 2 to the 192, there are in fact places in Urbit where you will load much larger conceptual natural numbers than this, right? Because 192 is what it's I don't know, it's some small number of bytes, but like if you load a text file, right, a Unix text file into Urbit, that'll be a byte array, and a byte array is an atom, and it's going to be a very large atom, much larger than 2 to the 192.
Mm-hmm.
Could
So
that just
there's
be? Can they just do like a big number encoding? Like there are known strategies for taking some type of fixed num
you
size
could,
and
yeah,
then
you
you
can,
know
but you would have to rather than doing it, you can't do it in the VM itself with this approach because the VM is over a particular finite field.
I mean, then
So you'd need to do it on top of it,
yeah,
which
my point
is
is that
fine
it
because
gives up.
you can host real Nock in Nock, which is nearly entirely transparent, and just have it not be transparent around atoms. So while they don't mention it, I can think of ways that I would do it.
So that you would just virtualize Nock and Nock, but actually implement big ints with whatever size finite field.
I would implement big ints using finite field elements. Yeah. Virtualizing Nock and Nock is by design very easy, right? If you run something in your Urbit REPL that's like actually about 5 levels of Nock and Nock, but they are all mostly transparent and they all call the VM the same way, and there's no reason you couldn't have a nearly transparent thing. One thing that you get in virtualized Nock and Nock is you get the extra 12 pseudo opcode, which does not exist in the VM, but it does exist in some virtualized levels.
What does that do?
12 is 12 is scry. 12 loads from the global Urbit network namespace, which is different from loading from the subject. It's sort of magic data from the sky. It's not actually in the real semantics of the language, but it will appear in some virtualization layer. And actually, the standard like virtualizer that you get in Hoon lets you supply your own implementation of some 12 opcode that you choose. But the one that you get in your REPL and in the whole system is the namespace cry.
Right. I had another kind of specific technical question, which is there's this part of the paper where they talk about how they actually link the program execution to the specific program is called with the specific input. And the way in which they do that requires, I mean, in the interactive version of the protocol, it requires sending the program and the input and the output to the verifier, which sort of renders the whole point of using a ZKVM moot. And I am assuming they do some kind of transform that then makes this like not a problem, but it was not super clear to me what it is.
Yes.
You know what part I'm talking about? Input output 7.2.
Yeah. 7.2. Yeah, no, I remember that. I think it's just not described in this paper if there's a way to do this. I think they're at least in this paper concerned more with can we prove the execution without doing the execution rather than can we conceal what was executed.
Yes, but I'm not, I don't mean from the privacy perspective. I just mean if the proof includes if for the proof to be a proof requires that you just include the computation, then I'm not sure what has been accomplished. Like,
Well, you include the result of the computation.
It says the prover sends the full computation. Oh, okay. So they just include the start and the end.
You include the input and output.
Right. I see.
Right.
I see.
You include subject, formula, and product.
I see. Then that is less bad. Presumably they replace it with commitments and
yeah, well, it's my understanding that you can do it. It's not particularly described in this paper, and I'm not particularly expert in the techniques used here, but it's my understanding that you can just replace those with commitments.
I see. Just I misunderstood. What they mean by full computation is not the trace.
Yeah.
It's just the input and output.
Yeah, it's just input output. Yeah.
Right. Okay. Yeah, it's cool. I mean, other than that, I like the paper. It's a nice demonstration of how the simplicity of Nock lends itself to, in some ways, a relatively simple arithmetization. There's a lot less complication here than there is in Mine or in Triton or something like this. Like there's just fewer tables, fewer special cased operations, and all this stuff.
Yeah, the special cased operation just consts more or less.
They have also, binary trees are a pretty structured data structure, like they're constrained, and this allows for efficient polynomial encodings. This kind of structure is excluded here. Although it wasn't, I mean, this paper doesn't include any benchmarks, and I feel like some of the things that they have to actually do, I mean, this is a lot of, I like Urbit Nock VM has some MIPS number, I'm assuming, like most programs are like how many rewrites, something like this.
Yeah, I don't remember off the top of my head, but people have done some various versions of the VM. I don't actually know what the current state of the art is.
Right. I mean, there still is I think it depends on like how many real program operations get per rewrite or something like this.
Like
how much does a branch cost, and memory accesses seem like they're not too
the bottleneck is always consing.
Right.
When implementing any sort of binary const cell based VM, consing is the expensive operation.
Isn't that more efficient these days? You mentioned that there was a second Urbit VM implementation that was making certain operations cheaper because they did realize what the bottleneck was. Wasn't there?
Yeah. I mean, since consing is always going to be the bottleneck, it provides it's an easy target to focus things on reducing the number of conses or making consing more efficient somehow. Both of which have been done, but I haven't kept up with the state of the art.
I guess I'll add one thing. Chris, you mentioned before that you worried about jets in particular and how they work. I assume a VM like this could give additional jets for field operations. So besides the standard set for, like, say, the CVM, you could provide certain operations. So field arithmetic and field access is quite cheap. I assume.
Yeah, I mean, I'm not worried about them being possible. I'm sure that they're possible. I'm, wondering how much complexity they will add and whether the whole resultant system like starts looking more and more like the typical complicated CKVM or not. That's all.
Yeah, I mean, when you jet things, the primary jets are arithmetic operations and so on, including finite field operations. There are some jets that are not actually performance necessary, but which are done as a form of fuzzing. Like crypto jets are like this. Well, I mean, they help with performance too. If you want real throughput, you would need the jet, but actually you are blocked by the slowness of consing long before you could get to real throughput. So in practice, the point of like the ED 25519 jet, for example, is more fuzzing than it is performance. So since I wrote the ED 25519 implementation, not all of it, like 2/3 of it, and I don't actually trust my own implementation. I think it's good that it's fuzzed, right? You can run the C reference implementation and my own implementation in together and check where they differ. But that's not. So it would be that's in a weird position where it would be performance necessary if consing were somehow cheaper, but actually you're bottlenecked by consing before you get to the point where it matters.
Yeah.
In terms of
I've
like weird high level things, like anything weird, more high level than a crypto primitive, jets basically don't exist for. I guess there are some in the compiler, but that's more of an artifact of the compiler having been a C program first
mhm.
to begin with. So the C implementation still survives in some form as jets.
Yeah, the other part here that I thought was like a little bit practically concerning is I mean, replacing nouns by hash is fine, but um, if you don't do it dynamically, I assume that basically it's very expensive to make proofs for programs where you have like repeated, um, you have a bunch of code beyond the standard library that you're just including all of the time. And in order to not include it all of the time in this form, you would have to build separate communication protocols for getting the verifier to know these other nouns, which I guess is relatively easy because they're just content addressable.
Yeah, they are just content addressable common subnouns. Like it's done with programs over the Orbit network outside of this VM context.
That's done over the air, like dynamically, or
yeah. Like generally, when two programs are talking to one another, they are the same program on both sides, or at least broadly similar programs, and they don't like transmit entire copies of their type definitions inefficiently.
right?
That would make packets very large.
Right.
Yeah.
Oh,
So they rely on some resolution being the same on both sides. In theory, you could do this even better with network paths, but that's not exactly what's done.
Nock Nock in general is, well, I guess Hoon in general is quite efficient on terms of like sharing subtrees, because otherwise it would be quite expensive to run anything if Zeus wasn't, for example, like shared between everybody. It would be quite bad.
Because this is the only project I'm aware of is Logan's project, which is this one.
Mm-hmm. Oh, it's cool. Besides leaving out a few details, I think it's a good paper. It's like pretty comprehensible.
Yeah.
Cool. Cool. Unless there's any other questions, I can call the recording done. Okay, great. Thank you everyone for coming to the Compilers Reading Group. The meetings are bi-weekly, or I guess once every 2 weeks. However, due to time constraints, they're kind of on demand. So if anyone has any presentations or would like to submit your own presentation, feel free to go to the thread, which is linked right here. You can see the website right in front of you right now. Just come to this link that you see above. Email me. My email is mariari@protonmail.ch, and just use the subject Compile Reading Group Suggestions. And we can set up a meeting with whatever you want. Yes, thank you for coming here.